Good morning, everybody. Thanks for joining us today. I'm happy to introduce this webinar by Haroldo de Campos Velho. Haroldo is a senior researcher at the National Institute for Space Research in Brazil. And the title of his presentation is Machine Learning Applied to Data Assimilation and the Prediction Geophysical Models. Before Haroldo presentation, I will present some slides on general information about CMCC. So CMCC is a foundation, and among the CMCC activities, one is to investigate and model our climate system and its interactions with society. And another active is to develop foresights and quantitative analysis of our future planet and the society. So CMCC is organized in the form of a network distributed throughout Italy. For instance, the CMCC has bases in the south in Lecce and also in the north of Italy, like Milano, Bologna, and Venezia. So there are some members and institutional partners which collaborate with CMCC, like the University of Salento, the University of Sassari, the Unibo, the University of Bologna, and the others. Now, CMCC is divided in research institute, like the Institute for Earth System and Predictions, the Institute for Climate Resilience, and the European Institute on Economics and the Environment. Since 2008, the CMCC Supercomputer Center is the most powerful computational facility in Italy, and among the most advanced in Europe, in the sense it is fully dedicated to climate change research. CMCC produces scientific articles for international journal. CMCC also promotes educational programs, events, communication, and dissemination activities for the public at large, like this webinar. So there are two different ways to interact with the presenter, with Haroldo. So you can ask questions using the question and answer section that you can see the bottom of the Zoom interface. And also you can use the raise hand option to. And as final remarks, this webinar will be recorded and uploaded on the CMCC YouTube channel. And finally, and also important, don't forget to follow CMCC on social media. Haroldo, thanks for coming and accepting this invitation. Now, the floor is yours. You can start the presentation. Thanks.
Thank you very much, Dr. Leonardo Lima. And I'm going to share my slides right now. Let me see here. Okay. Ok, buongiorno a tutti and good afternoon, maybe, if there is someone out of Europe. As Dr. Leonardo said, the title of my presentation is Machine Learning Applied to Data Accumulation and Prediction to Geophysical Models. I am Haroldo de Campos Velho, and I am from National Institute for Space Research here in Brazil. Well, the the outline of my presentation, I'm going to talk about machine learning for data assimilation, and we applied supervised or self-configuring neural network using multi-layer perceptron. And multi-layer perceptron is a configuration of multi-layer perceptron is addressed as optimization problem in order to identify the hyperparameters there. And our optimizer is multi-particle collision algorithm. And also another supervised neural network is deep learning, but neural network could be considered a kind of black box. But also you can apply another machine learning algorithm, for example, supervised decision tree. You are using this framework, XGBoost algorithm. And maybe it's not so a kind of black box, but I used to say is a white box. And also I'm going to do some words about we intend to do some cooperation between INPE and CMCC. This is under discussion, and I'm going to talk a little bit more about cascade data assimilation using standard or available data assimilation algorithms and multi-layer machine learning approach. And so you are going to do all of these algorithms together. One is based on in the standard or available data assimilation algorithm, and other is a new approach using machine learning. And so other approach is other topic of my talk here, it's machine learning to apply to predictability. And then my final topic of this presentation is hybrid prediction, how you combine differential equations for prediction and machine learning approach. I am from National Institute for Space Research. Okay, we have different unities around the country here in Brazil. And if you're not familiar with the geography in Brazil, the headquarters is in São José dos Campos. It's the main unity. And we have also in São Paulo state, in Atibaia town, and Cachoeira Paulista. By the way, Cachoeira Paulista, it is placed where we have the supercomputer facility here. And we have two unities in south of Brazil, Rio Grande do Sul state, and other unities in Mato Grosso, Cuiabá, and Belém, São Luís. This is the north part and the northwest part of Brazil. São Luís in Maranhão state, Eusébio in Ceará state, and Natal. Natal, it's in Rio Grande do Norte state. Okay, there is some facilities, for example, Muons detector and other radio telescopes, for example, Brazil, the symmetric array, other facilities is the spherical tokamak experiment, it's a plasma machine, and other, it's a combustion and propulsion laboratory, and monitoring deforestation, and numerical weather prediction. INPE is the institution provide to the country the numerical weather prediction to the nation. And a new activity here, it's space weather. And as you know, over the equator, you have this equatorial ionospheric anomaly. And this is a kind of feature where maybe GNSS, for example, GPS signal, it's not working over there. And we do some methods to predict the electronic content in the atmosphere. Some our results here. This is simulated electronic content, and this is observations. And this, for example, if you have drones flying over this region, probably this GPS sign is not working, so we need to do something else. Okay, in terms of data assimilation, the idea is to combine observations and model state in order to identify the best initial condition for your prediction cycle. And then you are going to do the forecast, and after And so the cycle of the prediction and assimilation observation is going to complete and start again. Okay, and so the idea is to combine model data and observations in order to produce initial conditions, and this is called a data assimilation process, as you know. But the idea here is to apply neural network, for example. And so we are going to use the supervised neural network, and our methodology is using supervised neural network, and the neural network is training to emulate another data assimilation technique. And why we're interested to emulate another technique? Because we are interested for saving processing time. As you know, data assimilation is very intensive computer process. And so the idea is try to identify other methodology, other algorithms in order to speeding up this process. And in order to do that, you need a database where you need a set of predictions, observations, and analysis. And you are going to emulate this analysis produced by other methodology. And also for global model, you apply the domain decomposition, where each domain have different neural network for producing data assimilation, okay? And our assimilation process, it's prepared to do some, producing some analysis for each model grid point. And as I said, we are going to do some automatic configuration for all of these neural networks. And then in terms of hyperparameter, we try to identify the number of hidden layers, the number of neurons for different layers, different hidden layers, and try to identify some other parameters for training phase, for example, momentum ratio and also the learning ratio. And also try to identify the type of activation function. Okay, here we are using tangent hyperbolic, logistic function, and Gaussian function, and that is our cost function to identify the best parameters for the neural network. And so you have the error for training, this part here, the generalization error. And so this is two subsets, and there is a penalty. This penalty here means because we are looking for the simplest neural network in order to produce the data assimilation. And the complexity here is measured by the number of neurons and also the number of epicals. Epicals, this is the number of iterations in order to complete your training phase. The solution, the optimizer for solving this optimization problem is a new particle collision algorithm, and this is available in the internet for free in this journal here. And this MPCA, for example, for Grievang function, when you're close to the minimal, the global minimum, there is a lot of local minima, and MPCA is very efficient in this kind of problems too. And so the idea, for example, we start with this global model for atmospheric model. This is a 3D spectral, the method for solving Navier-Stokes equation. It's a spectral method, and the idea is to emulate the ensemble Kalman filter. The ensemble Kalman filter is used for data assimilation, and you are going to training neural network to emulate this method. And all our results are published in this chapter of this book, Data Assimilation by Neural Network for atmospheric general circulation model. Okay, this is the equations. This is pretty standard in terms of vorticity and divergence, temperature, humidity. This is the equations for solving in order for this speedy model. This speedy model, it's interesting, but this is a very simplified parameterization approaches. That is our observation point here, collecting observations for this. And there we go. And so the two should be in the bottom of our slide here. And local ensemble transform Kalman filter, it's for temperature, temperature over the globe here. You can see the analysis produced by ensemble Kalman filter. On the right is neural network. Actually, this is pretty similar, these two analyses here, but there is a very important difference there, because the ensemble Kalman filter, this expand for this numerical experiment here, it's 4 hours and 20 minutes, hopefully, and neural network less than a half hour. And so other results using global model, it's we have presented this in IEEE World Congress on Computational Intelligence, happened in 2016 in Vancouver, Canada. And the idea is to also to apply for 3D atmospheric dynamic model. But in this model here, you are using the full parameterization for a physical process. And also, I applied this, well, we presented this result in this international symposium from the World Meteorological Organization. This occurred in Florianópolis, Brazil in 2017. And this, one of this person in charge of this symposium, it's Carla Cardinali. And Carla, we have no opportunity to meet that in this equation, in this symposium. And for this, Carla and I, we maintained some contacts, and I attending this conference here in Bologna in October. And this is the title of my presentation there. And I'm also, I stay in Bologna. I stayed in Bologna for 1 week more to discussing some topics of cooperation between INPE and CMCC, in particular, using machine learning for data assimilation. And then this is was invitation by the senior scientist, Carla Cardinali. She is the leader of the CMCC atmospheric data assimilation group. And cooperation topics is data assimilation by machine learning using cascade strategy, and uncertainty quantification. This is a possible topic for cooperation, and hybrid prediction. I'm going to present all of this. And so, as I said, in that symposium in Brazil in 2017, this is a global model from Florida State University. And in this application, we need to configure 96 neural network, because we need to divide the domain in 6 levels of the atmosphere, and also we divide the domain in four parts for the entire globe. And again, you can see here the surface produced by surface pressure produced by ensemble, the analysis for ensemble Kalman filter and neural network. And this is on the right side. is the difference between these two analyses. The green color here means that you are close to the zero. That's in other words, the analysis here is produced by two different methods are very similar, and for other variable, for example, specific humidity, you can see actually it's more, there are more similarities between these two analyses for this specific variable. You can see other variables, meteorological variables, but again, one important issue here is, for example, for ensemble common filter, for this numerical example, it's roughly about 27 hours, and using neural networks is a half hour. Okay, and but also you don't need to only to focus on in global model. If you're interested in regional model, limited area model, also you can apply this. For example, here you are going to do some comparison. The neural network is trained to emulate variational methods. Okay, and this is well, we applied for publication this neural network for data assimilation of surface and upper air data in Rio de Janeiro. This is a neural network is training for emulating the 3D VAR, three-dimensional variational method. And this is the region of our applications on Rio de Janeiro. And this is the difference between a neural network configured by MPCA and the variational methods for relative humidity, air temperature, wind component, in direction meridional component, and zonal component. And you can see that there is a lot of similarities between two methods. And so here, when you compare, for example, the analysis produced for 3D VAR and the analysis produced by neural network, it's close to the zero here. So this is on the right bottom on the right here. It's the difference between these two analyses, 3D VAR and MPCA. Okay, and then in order to have more clear what we're going to do here, it's if you were try to use, for example, the global data for your boundary conditions and initial condition. This is difference between prediction and observations. And so when you try to improve this using some observations in order to produce the analysis, you can clearly identify that you can reduce the difference between observation and prediction. But when you're trying to use different methods for data assimilation, for example, and so you can see here the blue line here represents the prediction by using data assimilation producing by neural network, deep learning here. And 3D VAR is the red curve here, and you can see that there is no data assimilation here. It's the yellow line here, and so you can see clearly the influence and the efficiency of data assimilation. But the neural network here, the analysis using the neural network here produce a better results for precipitation. And again, for in terms of this is a half hour for using 3D VAR, but half second using a half minute using neural network. And then summarizing what results that you have here for speed model, use an ensemble common filter in neural network, emulating ensemble common filter. the neural network was 95 times faster than ensemble common filters. For this global model from Florida State University, the neural network was 55 times faster than ensemble common filter. And this regional model, WRF from NCAR model, the neural network was 71 times faster than variational method. Okay, this is, I have only one example that it's a very simple example for ocean circulation. It's a shallow water 2D, actually a linearized model. And this is all parameters is set up in order to reproduce the ocean circulation. And our results you can access in this journal. This is available in the internet for free. Data assimilation by neural network for ocean simulation, the parallel implementation. And continuous line here represent the truth. Common filter and neural network here are representing by this dot lines. But in particular, neural network has this is two similar analysis, but neural network is a little bit better than common filter. But again, the difference here is for common filter, when you are trying to use 25 points of observation, this takes about 40 minutes using common filter. Using neural network, 1.5 minutes. But if you enhance the number of observations, for example, 100 points for observations, and then the data assimilation using common filter, this expand 1 hour and 20 minutes. And neural network, 5 minutes. Okay. But if you don't like neural network because you can see or can think that it's a kind of black box, my suggestion is you can try use another machine learning approach, machine learning algorithm. For example, using decision tree. Decision tree, you have a root node, and then there is some threshold in order to do for going to in this part of the decision tree, the left one or the right one, and this is another part of this decision tree. And then there is another decision node here, and again you have some different thresholds, and this is a kind of features that we're going to identify with this threshold in order to identify what you are going to classify. But here the decision tree it's applied as a regression model. Okay, and our approach is using this framework XGBoost. And XGBoost is a kind of, we are going to do some adding more and more decision tree. And so we start with a decision tree, you get some results, and then there is a kind of residual here. In order to reduce this residual, you can apply another decision tree, and you are going to adding some decision tree here in order to reducing this residual. And there you go. For example, this is the south of Brazil. I have some project try to derive some assimilation methods in different parts of Brazil using this regional, in very high resolution, regional atmospheric models, WRF. And this part is south of Brazil. Here is Uruguay, south of Brazil, part of Argentina, the north of Argentina, and south of Paraguay here. And this black dot here represents the observation points, okay? And again, This is the analysis produced by, this is temperature, surface temperature, by the way, and after atmospheric surface temperature. And this is the analysis produced by 3D VAR, and this is analysis produced by XGBoost. And here it's the difference between these two analyses. And then if you have only very strong blue here color, and then that means that the difference between these two analyses is going to be zero. But most part of this domain here, the analysis produced by these two different methods, two different approaches, is close to zero. And that is the one idea that we're going to apply here in our cooperation between INPE and this atmospheric group in CMCC. We are going to produce some kind of, I call it this pre-analysis, and pre-analysis are going to combine some observations and background using data assimilation that you have available in the CMCC. It's applying ensemble common filter, and this is the pre-analysis. And after this pre-analysis, you are going to combine other kind of observations using machine learning in order to produce the final analysis. Okay, that is one idea that I call it cascade data assimilation. Cascade because you are going to use two different methodologies for producing the analysis. In terms of data assimilation by agent-based models, this is a kind of survey and review produced in this journal, Mathematics. And in this table 5, there is 19 papers. This is in this survey, and these people from Australia, and the authors of this paper. These 19 papers, 14 papers, it's from my group here in INPE. Okay, and other applications of machine learning is hybrid prediction. This is our paper in Applied Computing in Geoscience journal, forecast of convective events by hybrid model, combining data from WRF model and machine learning algorithm. This is, well, we focus on Rio de Janeiro region. You can see 5 airports in this region here. And this is our domain. And in these 3 different domains, you have different resolutions there. In this red box here, we are going to use 2 kilometers for the simulation. And after the simulation prediction, using this differential equation model, WRF, you select some features, some inputs for our machine learning algorithm. And you are going to use the statistical analysis, call it p-value, in order to select the best. All idea here is try to reduce the dimension of the inputs of our machine learning. And then you can reduce, for example, 2 millions of possible inputs to 36. But this 36 has approximately similar information of these 2 millions of possible inputs. And you are going to, and we use this statistical analysis. This is hypothesis testing, calculating the p-value for each possible input. And this is this is a severe event happened in March 2021. And the green means that the algorithm, it's a correct prediction. and the red it's not so correct. And you can see here the multi-layer perceptron neural network has a better performance. And then that is we're producing, for example, some prediction by your atmospheric model based on the differential equations, and then you select some inputs in order to fit the machine learning model. And finally, predictability. Okay, and so data assimilation is a kind of pre-processing in order to identify the best initial condition. And then you apply this for producing your prediction, your forecasting. Okay, after that, you have your prediction. How good is your prediction? How can you identify where and when this prediction is good or more comfortable? And then, for example, you can use a kind of Monte Carlo approach, ensemble prediction. And ensemble prediction, you can identify high predictability zones when all of this ensemble has a very small variance. But when this ensemble have a bigger or larger variance, and then this is a zone of low predictability. Okay, and so you can compute your confidence interval and use this neural network for this neural network emulate the average of the ensemble, and then you are going to after to generate the configured neural network for that, and you are going to apply it for different members of this ensemble. For example, and this is a local ensemble common filter, and this is the control. Here is the temperature produced by neural network. This is control. And again, the results here for prediction, it's very similar for ensemble common filter or neural network for data assimilation. And of course, when you are going to, for long period for prediction, the uncertainties or the confidence interval is going to be very large, as you can see here. Okay, but you can do something different. For example, you are predicting, if you using for your prediction neural network or for data assimilation, doesn't matter. The idea is to configure machine learning to predict also this uncertainty. And this uncertainty, you are going to prediction the variance associated to this predictability or uncertainties in your prediction. We show that this approach in this uncertainties workshop happened in 2023 in July, and this is the fit our methods using decision tree here to quantify the uncertainties in our prediction. And the prediction, this is in climate precipitation climate prediction, okay, for the South America. And this is the observations. The database is GPCP, and this is precipitation predicted by decision tree. And here is the error or the uncertainties, the exact uncertainty, and this is the predict uncertainty using decision tree. Okay, and for all of these ideas, some of these ideas, you can see in this short course on data assimilation. This happened in July 2022, and all of this short course is available on the internet in YouTube. And well, you can implement this in different architectures, for example, FPGA and other architecture. Hardware architecture is this tensor processing unity Again, this is data assimilation using CPU for neural network, and this tensor processing unity. And when it enhance the number of grid points in your model, and then TPU, it's more effective than CPU. But basically, this is the idea. And we have new hardware, not using electrons, but using photons. And this is one supercomputer with photonic processor. Maybe this is the new age of the computers. Okay, finally, let me to address some final remarks. Machine learning is a new wave of many applications with good results. We just giving our first steps here on this new methodology. A strong motivation to apply machine learning technique to geophysical models, because you are going to do this strongly reducing the computer effort. Two applications very computer intensive and deserve more investigation. One is data assimilation. It's a pre-processing for our pre-processing for our methods for forecasting. And predictability. This is try to identify or to quantify the uncertainties in our prediction. This is a kind of post-processing. One important application that I'm very interested here in Brazil, it's hybrid prediction, combining differential equation models and machine learning models or data-driven model. Thank you very much for your attention, and I'm open for your comments, questions. Okay, thank you very much, all of you, and in particular for this invitation from CMC, Dr. Leonardo. Okay.
Thanks a lot, Haroldo. Let's see if you don't have questions on the question and answers section, but I mean, if somebody has questions, you can. This is the time for questions. So, Haroldo, I have a question because I've seen your results, and there is no doubt that the machine learning techniques, as you have applied, it reduces the time for the computational time for preparing the analysis. But have you investigated the impact on the forecast in terms of numbers, the quality of the forecast using the machine learning technique with respect to the forecast derived from the conventional data simulation itself?
Well, when I show you that results using this regional model, WRF from NCAR, developed by NCAR, I'm not showing the difference between two analyses. I'm showing the difference between predictions. And then one week ahead, 7 days. And then that is the average. When I show you, let me show again. Thank you for the question. I think that it's one important question for that. Here. Okay, I'm going to share again my slide here. Okay, and so here we're going to see here, it's the prediction. This is prediction when you're using, for example, boundary conditions and initial conditions from global model, okay? And so that is the error for this air temperature average. In this, we are going to do some 24-hour prediction. And so 24 hours for day 1, day 2, up to day 7, okay? Thank you, because in my in my presentation, I don't pay attention for that. And then that is the difference in average for the air temperature from the background and the observation. But you are not using any kind of data assimilation here. And then you are going to use some of the assimilation. And this is the difference between this variational method for data assimilation and observations. Okay, you can see here in these red points, it's 5 points that you are collecting observation here. Okay, this is from airports in this region here. Okay, that is, and you clearly you can see that you improve your prediction if you use data assimilation here. Okay, but this is prediction. It's not the analysis. This is the prediction, and this is the impact of the analysis on prediction, on forecasting. Okay, thank you for your question again. Okay, and so when you put all together, that is in the yellow curve here, it's the error of, or the difference between observations and prediction for an average of, this is 4 days, 7 days. And this 7 days in average, that the difference, it's the yellow line here. But using a variational method, it's the red line here. By the way, the troposphere here, it's stopped in this 10 kilometers for the atmosphere. Okay, and using neural network, this is the blue line here. And so the blue line, it's very similar in terms of the impact of prediction. The blue line, it's very close to the red line here, and in terms of reducing the error of the prediction. But the error using neural network here, it's smaller than variational method, 3D variational method here. But not only this, it's not better in terms of impact of prediction. That means you have a better prediction if you're using neural network data assimilation. But also, imagine this time reduction here, a half hour using variational method and a half minute using neural network. Thank you for your question. I think that this has helped me to clarify this point here, the impact of data assimilation. We know that data assimilation, it's important in order to improve the forecasting. But this is result using neural network and variational method. Both methods can improve your forecasting. However, the neural network here, it's better than the method that is trained to emulate it. Secondly, this is a very strong computer effort for producing the analysis. Okay, Leonardo, thank you. I appreciate your question.
Thanks a lot, Haroldo. So now we have a few questions on the question and answer section. First, one question from Justin. Can machine learning be used for data simulation and prediction of environmental disasters?
Yes, actually, we are interested. We start to use this WRF because we are looking for the prediction in now casting, in few hours up to 24 hours, in particular for aviation meteorology. In aviation meteorology, we are looking for a very intensive convective events. And then this severe weather, this is one issue that we have interested. And by the way, this is one example using that I'm showing here with after the question from Dr. Leonardo Lima here. This is a good opportunity to clarify some question here. And yes, then my answer is totally yes. And secondly, it's Igor Ataki. This is the first question from Justine, and here it's Igor Ataki. When you are using XGBoost to have a better interpretability, yes. What are the methods to do that? Does it make it easier to understand the role of the more or less relevant environmental variables? Absolutely. And then, Igor, as you know, for example, when we have different features, different inputs, and then you are going to classify how the importance, the influence of these different inputs for your to fit it as a new scheme to fit our decision tree. And then one method to identify is the gain of information using the Shannon entropy. And this gain of entropy, the gain of entropy, this gain of information, it's going to identify or classify the importance, the relevance for different inputs for feeding our machine learning. And so that is. And so for this, as you said, it's a better interpretability. I used to say this is a kind of white box because you identify different from neural network because you don't have a very clear the importance, the relevance of different inputs. But in decision tree, you have this in order to select who is the root. And then the root is the more important, the more relevance of our input. And yes, again, this is, I used to say, white box. Leonardo Aragão, Haroldo, thanks for the presentation. Thank you for attending here. And was data assimilation performed independently by processing inputs or internally using the WRF data? Okay, this is it's performed independently. Well, we have two different models, and model for variational method and model for neural network. And then this is two independent models, and you prepare initial condition for the prediction. And Geoff Doschaffer, this time of 25 minutes after training, yes, because you are going to use how much time do you spend training the model? It's a few days, depending on the model, depending on the number of grid points that you are in your. But this is takes about few days. But actually, I don't take into account this because during the operational issues, operational activity, you are not training your neural network. The neural network is already trained, and then operational activity, you need to focus on how long the effort for in operational activity, the CPU time that you are going to use this procedure for producing the analysis. And Kaima, Mohammed, how data assimilation can be used to carbon accounting and which feature must be focused on? Yes, this is one thing that we're going to actually, there is an important this. Thank you for your question here, by the way. We have one discussions in terms of cooperation with the International Center for Theoretical Physics in Trieste, also in Italy, and they are trying to interested to some climate change. In terms of climate change, one idea is to use this environmental prediction, for example, CO2 or other minority gas, but it's very important in terms of minority, but it's very important for climate change, by the way. And one thing that's interested, because Brazil, INPE, it's not only produce the weather prediction, climate prediction, ocean wave prediction, but also environmental prediction. Actually, INPE, the National Institute for Spatial Research here in Brazil, was the first institute to do this operational environmental prediction. And this is very consuming, and also for data assimilation for that, it's we are preparing for aerosol and this chemical prediction in terms of environmental prediction. This is very expensive, and then we are going to apply this. Yes, we don't have results here, Kaimar, but this is we're maybe the idea is to have some next year in 2024. Probably we have good results. I mean, first results. Not, I don't know if it's good or bad, but it's first results is going to produce in the next year. Thomas, thanks for the presentation. Very interesting results. In addition to quantify the future importance, have you also looked at applying more involved methods to explain why the model performs the way it does, and perhaps improve our physical understanding, for example, symbolic regression or some approach? No, well, no, I'm not using symbolic regression, but I'm fully interested in other. For example, one thing that we're interested here, I just show you some results using a supervised neural network, but the idea is to using other methodologies, unsupervised methodology, for example. This is one thing that we are going to explore together with the people from CMCC group, where Carla Cardinale is the leader. One idea that we are going to work together is exactly to develop these new methods, unsupervised methods, in terms of machine learning algorithm to address on this, but not for in terms of symbolic regression, unfortunately not, Thomas. But thank you for your question. Karina, sorry, I don't hear. Are the temperature profiles you show global ones? Yes, for some results using global models, and for WRF not. It's only for the Rio de Janeiro region here, around of the Rio de Janeiro city. Well, thanks for your questions and clarify something. This helped me to clarify some points in my presentation. Thank you for, and I hope that you will address your questions and comments.
Okay, so we're almost about 1 p.m. Thank you, Haroldo, for accepting the invitation. Thanks again. Thanks, Agnes, and also Antonella for the support. And yes, that's it. Now you can close. And thanks for your presence.
Okay, thank you for this invitation, and also thank you for this support team here from CMCC. Thank you a lot, and have a good day.